All right, so today we're tackling something pretty massive, like universe-level massive. We're diving into Einstein's theory of general relativity.
Oh, yeah, that's the one about gravity and space-time being all warped and wibbly-wobbly,
Yeah,
right?
exactly. It's been around for over a century
Hmm.
and has pretty much shaped how we understand the universe.
Yeah.
But there's a but.
Always a but, isn't there?
Uh-huh, right.
Yeah.
So, some recent findings are kind of suggesting it might not be the whole picture.
Really? Like, is it wrong? Or just incomplete?
Well, that's what we're going to unpack. Our guide for this deep dive is this research article from scitechdaily.com. It's called, Is the Universe Defying Einstein? New Discoveries Challenge Relativity. Pretty catchy title, huh?
Definitely grabs your attention. And what's the source for this? Like, who did the research?
It's based on findings from the University of Geneva and also Toulouse III, Paul Sabatier,
Oh.
and they published their work in Nature Communications.
Ah, okay, heavy hitters. So what's the gist? Like, what exactly are they challenging about Einstein's theory?
So they're suggesting that gravity might act a little differently over really vast distances. And you know what that means.
Black holes, the Big Bang, pretty much all our cosmological models might need a rethink.
Bingo. All right, let's get into the nitty-gritty. The article kicks off with this project called the Dark Energy Survey. They're mapping out like millions of galaxies.
I've heard of that. Isn't the goal to figure out what the universe is made of and how it's changed over time?
Yeah. And their data is amazing. It's basically a time machine, letting us look back billions of years.
Wow. Okay, so how does this relate to Einstein's theory being challenged?
Well, the researchers took a close look at about 100 million galaxies. They were specifically studying how these galaxies get distorted. It's called gravitational lensing.
Ah, right. That's where massive objects like bend light. Classic Einstein.
And for the most part, the observations matched up with Einstein's predictions, at least for stuff that happened way back, about 6 to 7 billion years ago.
Okay, so what changed? When did things start getting weird?
Things got interesting when they looked at more recent data, closer to like 3.5 to 5 billion years ago.
Oh, and what did they see?
The gravitational wells, those like dips in space-time, they seemed shallower than Einstein predicted. It's like gravity wasn't as strong as it should have been.
Whoa.
And so gravity might not be constant throughout the entire universe. Whoa.
That's the million-dollar question, isn't it? And the discrepancy they found, it wasn't just a fluke. It was statistically significant.
Statistically significant. Can you elaborate on that a bit for those of us who aren't like statisticians?
Sure. So basically it means the chance of this being just random noise is super low, about 1 in 740.
So not impossible, but.
Right. In physics, we usually want a higher level of certainty, but this is definitely raising eyebrows.
So Einstein is not completely wrong, but
there might be something more to the story, like a missing piece of the puzzle.
and that's where things get really mind-blowing, right? This ties into something we kind of touched on earlier.
You mean the fact that the universe is expanding?
Well, not just expanding, but expanding faster and faster. The acceleration is what's key.
Ah, right. Dark energy, the mysterious force that's pushing everything apart.
So how does that connect to these, like, weaker gravitational wells? Could they be related?
Some physicists think so. They're saying maybe dark energy isn't just pushing things apart. It's messing with gravity itself at these massive cosmic scales.
So it's like a constant tug of war between gravity trying to pull everything together and this dark energy pushing everything away.
And that cosmic battle might be influencing how strong gravity actually is.
So maybe Einstein's theory isn't wrong. It's just, like you said earlier, incomplete.
Yeah, maybe it needs an update, something to account for dark energy. Kind of like how Newton's laws were fine until we started looking at like really fast speeds and super strong gravity.
So we needed Einstein to come in and give us a more complete picture.
Exactly. And now we might be at a similar point where we need to go even further than Einstein.
All right, so if this is true, if we really do need to revise our understanding of gravity, what does that mean for, well, everything, like specifically?
Well, for starters, our picture of black holes might need a total makeover.
Oh, right. Black holes, those things that are so dense even light can't escape.
Yeah, and we've always used Einstein's theories to explain how they form and what happens inside them. But if gravity works differently on super large scales...
Then our black hole models might be way off. Okay, that's pretty trippy. What else?
The Big Bang, too. Our understanding of the very beginning of the universe hinges on general relativity.
So if we change the foundation, everything built on top of it changes too.
Exactly. We might have to rethink our whole cosmological model.
This is heavy stuff.
It is, but that's the beauty of science. We
Yeah.
question, we refine, we learn. And thankfully, we've got a new tool to help us figure this all out. The Euclid Space Telescope.
Oh yeah, the Euclid mission. You mentioned it earlier. What's the deal with that?
Well, it launched just last year, and its whole mission is to study dark energy and how it affects the universe.
How does it do that? Like, what's so special about this telescope?
It's going to map out, get this, 1.5 billion galaxies over the next 6 years.
Whoa, 1.5 billion?
Yeah.
That's a lot of galaxies.
It is. And it'll measure their shapes super precisely, giving us the most detailed map of the universe's gravitational landscape ever.
So we can compare that data to what Einstein predicted and maybe finally figure out if gravity is really acting up at these vast distances.
That's the hope. Euclid will be sensitive enough to either confirm what the dark energy survey found or maybe disprove it. Either way, it's going to teach us a lot.
Man, this is like being on the verge of a scientific breakthrough. I love this feeling.
It is exciting. But before we get lost in all the possibilities, let's recap what we know so far, just to make sure everyone's on the same page.
Yeah, good idea. What are the key takeaways so far?
All right, so we started with Einstein's theory of general relativity, this groundbreaking idea that massive objects warp space-time, creating these things called gravitational wells that can actually bend light.
And that bending of light is called gravitational lensing, right?
Mm-hmm.
That's how the Dark Energy Survey was able to map out the universe's gravity.
Exactly. But the problem is, they found this discrepancy. Stuff in the early universe fit Einstein's predictions pretty well, but more recent stuff, not so much.
Right, those gravitational wells were shallower, meaning gravity seemed weaker than expected.
And that led to this wild idea that maybe, just maybe, it's connected to dark energy, that force that's causing the universe to expand faster and faster.
Right, like they're both fighting for control, and the outcome of that battle is affecting how strong gravity is.
And that brings us to the Euclid mission, which is poised to either confirm or deny this whole idea.
So, by looking at billions of galaxies, it'll create this insanely detailed 3D map, tracking how the universe has changed over billions of years, and maybe revealing the fingerprints of dark energy all over it.
Precisely. It's going to be groundbreaking.
This is like mind-blowing stuff.
It really is, and it makes you realize how much we still don't know about the universe.
Exactly. I mean, all the stars and galaxies we can see, they only make up a tiny fraction of everything. Most of it is this dark matter and dark energy that we're still trying to figure out.
It's a humbling reminder that we're just scratching the surface.
Okay, before we dive deeper into the mysteries of dark energy, let's take a quick break. We'll be back in a moment to explore the different theories about what this mysterious force might actually be.
Sounds good. Stay tuned. All right, so where were we? Yes, dark energy. It's a pretty big deal, to say the least.
Yeah, like it literally shaping the fate of the entire universe, but we barely know anything about it.
Yeah.
So let's get into it. What are the leading theories about what this mysterious force actually is?
Well, one of the most popular ideas is that it's not really a force in the traditional sense, but more like a property of space itself.
A property of space. What does that even mean?
It's like space has this built-in energy that creates a kind of negative pressure.
Negative pressure. Okay, my brain just did a somersault.
I know, it's weird to think about. Usually pressure pushes things inward, right? Like in a balloon.
Right.
But with dark energy, it's the opposite. It pushes outward.
So it's like the universe is this giant balloon that's constantly being blown up, pushing everything farther apart.
That's a pretty good analogy. And here's the kicker. The more space expands, the more dark energy there is because it's like woven into the fabric of space itself.
So the more the universe expands, the faster it expands. That's both amazing and kind of scary. Like, where does it all end?
Well, that's a question that keeps cosmologists up at night. Some think this could lead to a scenario called the Big Rip.
The Big Rip. Sounds dramatic.
It is. Basically, the expansion would get so strong that it tears apart everything. Galaxies, stars, planets, even atoms.
Whoa. Okay, so one possible ending is that everything just, like, disintegrates.
It's a possibility, but remember, this is just one theory. We're still figuring all this stuff out.
Okay, good, because that's a little too intense, even for me.
Yeah.
So what are some other theories about dark energy?
Another idea is that it's a new kind of field that permeates all of space. It's sometimes called quintessence.
Quintessence. Sounds fancy.
It does, right? The key difference here is that this field wouldn't be constant. Its energy density could change over time.
So unlike the space itself theory, this one says dark energy could, like, fluctuate.
Yeah, which would mean the universe's expansion might not accelerate forever. Maybe it slows down at some point or even reverses.
Okay, so we've got the space itself theory, the dynamic field theory. Any other wild ideas out there?
Well, some physicists are proposing something even more radical. They say maybe we need to rethink gravity entirely. Like maybe Einstein's theory needs a major overhaul.
Wait, so you're saying dark energy might not even exist?
Potentially, it could be that our understanding of gravity is just incomplete, and that's what's causing this apparent acceleration.
So dark energy could just be an illusion created by our own limited knowledge. That's a pretty big thought.
It is. But changing our whole understanding of gravity is a big deal. It would have to explain everything else we've observed about the universe, too.
Right, it can't just solve one problem and create a bunch of new ones.
Exactly. It's a tricky puzzle, but some smart people are working on it.
Well, it's mind-blowing to think that we still don't know what this stuff is, even though it makes up most of the universe.
Yeah,
But I guess that's what makes cosmology so fascinating.
absolutely. It's all about exploring the unknown, pushing the boundaries of our knowledge.
So let's bring it back to this Euclid mission. You said it's going to help us understand dark energy better. But how? What's it going to do that's so special?
Well, Euclid will be using a couple of cool tricks. One of them is called baryonic acoustic oscillations.
Whoa, hold on, what? Baryonic acoustic oscillations? That sounds super complicated.
It's not as bad as it sounds, I promise. It all starts with the early universe, right after the Big Bang. It was this incredibly hot and dense soup of particles, and there were sound waves rippling through it.
So the early universe was like one giant cosmic orchestra.
Exactly. And those sound waves, they weren't just traveling through the stuff in the universe, they were traveling through space-time itself. And as the universe expanded and cooled down, those sound waves left an imprint, a sort of pattern, in how matter is distributed.
So they're like cosmic fossils from the Big Bang.
Perfect analogy. And by measuring the size and spacing of these fossils, Euclid can figure out how fast the universe was expanding at different points in time.
And that tells us about dark energy.
Exactly. We can see how dark energy has been affecting the expansion rate over billions of years.
Wow, that's pretty clever. Using these ancient echoes to track dark energy. What's the other thing Euclid's going to do?
The other technique is called weak gravitational lensing.
Ah, right. We talked about that earlier. That's where gravity bends light.
Yep. But Euclid will be able to measure these distortions with incredible precision. It's going to look at the shapes of billions of galaxies and how their light is bent by the gravity of stuff in between.
So it's like using the distortions to map out where dark matter and dark energy are lurking.
Exactly. By combining these two methods, baryonic acoustic oscillations and weak gravitational lensing, Euclid will create a super detailed 3D map of the universe. And that map will show us how dark energy has been shaping things over billions of years.
This is so cool. I can see why everyone's excited about Euclid.
It's going to be a game changer, no doubt. And the best part is, we don't have to wait too long. Euclid is already out there collecting data, and the first results should be coming in pretty soon.
I can't wait to see what they find.
Yeah.
Okay, so before we get totally lost in space, can we do a quick recap about the Euclid mission?
Sure thing. So Euclid is a space telescope that launched in 2023. Its main job is to study dark energy and its effects on the universe. And it's going to do that by using these two main techniques: baryonic acoustic oscillations and weak gravitational lensing.
Right, so by looking at these subtle patterns in how matter and light are distributed, Euclid will create a 3D map of the universe. And that map will show how dark energy has been playing a role in shaping the universe over billions of years.
Precisely. Euclid is going to be a major achievement, and its data will keep scientists busy for decades to come.
This is all so incredible. We started by talking about how Einstein's theory might need some modifications because of dark energy.
And then we went through all these crazy theories about what dark energy could be. A property of space, a dynamic field, or maybe even a sign that we need to completely rethink gravity.
And then we got into the Euclid mission, which is going to help us solve some of these mysteries.
It's been quite a journey so far, and it really highlights how much we still don't know about the universe.
You know, it's pretty humbling to realize that all the stars and galaxies we can see only make up about 5% of the universe. The rest is dark matter and dark energy, which we're still trying to wrap our heads around.
It's a reminder that we're just beginning to explore the universe and that there's so much more to discover.
Exactly. So where do we go from here? What are the big questions that cosmologists are wrestling with right now?
Well, figuring out dark energy is still top of the list. We've talked about some of the possibilities, but we're nowhere near a definitive answer.
It's like we've identified this force that's controlling the universe's destiny, but we still don't know what it really is. So what other big questions are out there?
Another major one is the nature of dark matter. We haven't talked about it much today, but it's another one of these invisible things that makes up a huge chunk of the universe.
Oh yeah, dark matter. I remember learning about it in school, but I'll admit it's always been a bit hazy in my mind. Can you give me a refresher?
Sure. Dark matter is this invisible stuff that doesn't interact with light, so we can't see it directly. But we know it's there because of its gravity.
Wait, so how do we know it exists if we can't see it?
We can see its effects. Like if you look at how galaxies rotate, they spin much faster than they should based on the stuff we can see.
So they're spinning too fast for their own good.
Pretty much. And the only way to explain that is if there's a lot more mass out there that we can't see that's dark matter. It's like the invisible scaffolding that holds galaxies together.
So we've got this invisible stuff holding galaxies together and this other invisible stuff pushing everything apart. My brain is officially fried.
I hear you. But it's exciting stuff. We live in this incredible time where we have the technology to actually study these mysteries.
That's true. We're on the cusp of making some major discoveries, and it feels like anything is possible.
Absolutely. The next few decades could be revolutionary for our understanding of the universe and our place in it.
This whole conversation has really shifted my perspective. I feel like I've zoomed out from everyday life and got a glimpse of how vast and complex the universe really is.
I know what you mean. When you start thinking about these big questions, it can really change how you see the world. It's a reminder of how much we still don't know, but also how much there is to discover.
It's like we're exploring a vast, uncharted territory, and we're just starting to scratch the surface.
And the map is constantly changing as we make new discoveries and refine our understanding. It's an adventure that never ends.
Okay, so we've covered dark energy and dark matter. What other mind-blowing mysteries are cosmologists working on?
Well, another fascinating area of research is the very early universe, like the first few fractions of a second after the Big Bang.
Whoa, we're going way back in time now. What's so special about those first few moments?
Well, in those initial moments, the universe was incredibly hot and dense, and it's thought that all the fundamental forces of nature were unified.
So it's like trying to peek into the universe's baby pictures.
Exactly. And those baby pictures could hold clues to some of the universe's deepest secrets, like how it all began and what the fundamental laws of physics really are.
Okay, before my brain melts from too much cosmic information, can we quickly recap these big questions we've been discussing?
Sure. We started by trying to figure out dark energy and dark matter, those invisible forces that make up most of the universe.
Right, those are the big unknowns we're still trying to solve.
And then we went way back in time to the very early universe, that first fraction of a second after the Big Bang, to understand how the universe evolved into what we see today.
Like trying to rewind the cosmic clock to figure out the universe's origin story.
Precisely. And those early moments could reveal some of the most fundamental secrets of the universe.
This has been such an incredible conversation. I feel like I've learned so much about the universe and all the amazing work that scientists are doing to understand it.
It's been a pleasure to share my passion for cosmology with you, and hopefully it sparked some curiosity in our listeners, too.
I have a feeling they're going to have a ton of questions after this deep dive.
Yeah.
But before we wrap up, I want to leave them with something to ponder.
Ooh, I like that. A little food for thought.
So we've spent all this time talking about these huge cosmic mysteries, dark energy, dark matter, the Big Bang. But what if the biggest mystery is something closer to home?
Closer to home, what do you mean?
Well, what if the answer to dark energy isn't some exotic new physics, but something more fundamental, like gravity itself?
Ah, I see where you're going with this. You're suggesting maybe we don't need dark energy at all.
Exactly. We already talked about how Einstein's theory might need some tweaks. What if those tweaks, instead of pointing to dark energy, actually lead us to a deeper understanding of gravity? One that explains the accelerating expansion without this mysterious extra force.
That's a pretty radical idea, but it wouldn't be the first time we had to rethink gravity, right? I mean, think about Newton. His laws worked great for ages until Einstein came along.
Right. Einstein showed us that gravity wasn't just a force, but a curvature of space-time. So who's to say Einstein had the final word? Maybe there's an even deeper level of understanding waiting to be uncovered, something that could unite gravity with all the other forces in the universe.
Now that would be a game changer. A unified theory of everything, that's the holy grail for physicists. And you're saying the key might lie in understanding dark energy and its link to gravity.
It's wild, right? This thing that we thought was pushing the universe apart might actually be telling us something profound about how gravity really works.
It's a reminder that sometimes the most mind-blowing answers are hidden in plain sight. We just have to ask the right questions.
And that's what science is all about, right?
Yeah.
Questioning everything, pushing the boundaries.
Absolutely. It's a journey that never really ends. There's always something new to discover.
Well, this deep dive has definitely left me with more questions than answers.
That's a good thing. It means we've sparked your curiosity, made you think about things in a new way.
It definitely has. And I think that's a great place to wrap things up.
Yeah, I think so too.
To all our listeners, thanks for joining us on this wild ride through the cosmos. I hope you enjoyed exploring the mysteries of the universe as much as we did.
And remember, the universe is full of wonders. So keep looking up, keep asking questions, and never stop exploring.